Okay, welcome everyone to this continuation of what is algebraic geometry. Today I would continue to talk about schemes, and yeah, it gets a bit annoying. Why is it annoying to talk about schemes? Well, because there's always just a slight difference to the affine variety or to the variety story. And this difference is crucial, and I will stress that a lot, the little difference. And then the rest go through. So it's somehow not really annoying to talk about them. It's actually pretty brilliant. It's kind of a generalization where everything goes through. So if you want to think about a metric generalizing kind of Euclidean distance, and somehow everything goes through. So it's kind of a very, very much more generality. And the only thing that makes it a bit annoying for me is, the only thing I really then have to say is I have to stress the little difference. And the rest is the same as before. So, yeah. Anyway, so here the difference, and I hope I make that clear in an example, will be how to divide without a field. So in some sense, always think about a scheme that we don't like the ground field anymore. We kind of want to do it for all ground fields at the same time. So whenever one of the constructions we have seen for varieties has something to do with a ground field, we need to be a bit careful, right? That's a kind of the slight difference. And yeah, regular functions, as a reminder, had some ground field going on. There was a map to the ground field. But if you want to ignore the ground field, how do we do that? Yeah, let's see what we do. Okay, so what to do without a field? It's kind of the same. It's kind of the same question. Let me say that again. Scheme is like a kind of field-free version of a variety. And one of the crucial things we had on a variety were regular functions. Without recalling what they are up here. Essentially, they were f divided by g, a regular function, polynomial divided by polynomial, whatever. Something like an x squared minus y divided by y minus 1, something like that. Some regular function. But they were only regular because regular functions are rare on varieties, or they're kind of too strong on varieties. That's maybe the right way of saying it. They're only locally regular. So they're regular on some open subset. Okay, fine. So there are two problems with this definition because our little scheme is just completely ground field free. It's just spec R plus the risky topology. And you can clearly see here the regular function is a map to the ground field, and then it's a quotient in the ground field. And both kind of things don't really make sense, right? So we don't have a ground field, no ground field. Sorry, I shouldn't have crossed out the ground field in the affine world. No ground field in the scheme world. So what does it even mean if you don't have any ground field? And turns out that's why it was annoying. Coming back to that, as soon as we have understood what that means, everything again goes through as for the regular functions. You have a sheaf of regular functions, you have a ring of regular functions, and whatnot. But first, let's understand this problem, or let's see how we can reformulate that problem. So the way how to reformulate is to use the theorem which we had about regular functions. So the ring of regular functions is actually nothing else than a localization of the coordinate ring. Yeah. And if you think about a scheme again, so let's go back to the schemes. Okay, they're k-free, but they also replace the coordinate ring, which clearly depends on k, with the general ring, right? So coordinate ring, general ring, fine. And now here we had the statement that the ring of regular functions is isomorphic to a localization of a coordinate ring. Yeah? So really like Laurent polynomials on the coordinate ring. That's what it should be, because you have quotients like f over g, right? But that somehow now makes completely sense in a ring theoretical world. We can localize a ring and a nice ideal. So that's what you usually do in algebra. And nice ideal would be something like a prime ideal. And oh, wait, we do have prime ideals. So maybe that's what we want to do. I say that again. It's the same story. Scheme is always reformulated in terms of a ring theoretic property. Take that as a definition, take it from there. Okay? So here, the regular function problem, I don't know what a ground field is. That's a bit of a problem. But I know that this thing is isomorphic to a localization. Localization is the ring theoretical thing. So why not take that as a definition? Take this as a scheme theoretic scheme theoretic definition. That's more difficult to pronounce than you think. Scheme theoretic definition of of what a regular function is supposed to be. Yeah, so really it's about fractions, and the localization just makes sense with any prime ideal. So you can just localize around it. You get a local, you get something like this ring localized at R. Yeah, sure. The ring localized at a certain set, and usually a prime ideal is exactly what you want to localize at. And this is like the ring theoretical version of mimicking fractions. So what you should do, what should be a regular function be? It should be take an open subset of R spec R, which contains prime ideals. That's how the subsets are defined. And a regular function should be now a collection, because it's local, of fractions. Yeah. And what is a fraction? A fraction is just an element of localization. So our prime ideals, everything works out. That should be a regular function, and we essentially define that as a regular function. On the next slide, I just write down all the funny details which you can mostly ignore. I hope this is kind of clear. Instead of having local fractions, which takes values in the field which you don't know what to do with, we go to the ring theoretical side, and we just say a regular function is a collection of elements in a localization. It's not really a function anymore, right? It's kind of a collection of elements in the localization. That's still a function in a certain sense, but it's not in any straightforward sense a function. We kind of replaced it by something that looks different, but is somewhat isomorphic in flavor, at least, and even isomorphic if you zoom into affine varieties. So I don't say that anymore, but any scheme theoretical definition, if you take R to be the coordinate ring of a variety, gives you back what you have seen before, right? That's kind of the point. So here is the definition if you want to read it. If not, it really just says it's a collection of elements locally, of local elements in localization. So local means here on open subsets, and localization is slightly different. Don't get that too confused. Local refers to the open subset property, and localization is a fraction. So that's what I want to say. And then everything goes through. And kind of the brilliant thing here is not to think about a function anymore, but now a collection of elements in a localization. Okay. Yeah. And you get the same story, ring of regular functions, sheaf of regular functions, whatever not. Let's rather have a look at an example, and I leave it to you to just pause the video or go to your favorite source and read it. So our favorite example was this one, and we are, by the way, still down here. Spec of the integers. So spec of the integers contains the prime ideals, which is 2, 3, 5, 7, whatever, prime numbers, and 0. 0 is the corresponding one to Q, so characteristic 0. And otherwise characteristic 2, 3, 5, 7, kind of all characteristics at once, right? We do it characteristic 3, we do it ground ring 3. Yeah, and spec Z is kind of the prime example, the prototypical example of an affine scheme. And I consider the distinguished open set. Yeah, so distinguished open sets, remember we had them in variety world, and you can find them in the same way. And let me just give you an example here. The distinguished open set around 6 would be the ideal 0 and the ideals P, with P not 2 and 3. But 2 and 3 are bad, they're the prime divisors of 6. So that doesn't quite work, so you just take the other ones. And then the fraction, it's kind of fun now, the fraction 5 over 6 is now a regular function. The fraction 5 over 6 is a regular function, right? We now have replaced the function by just a collection of 5 over 6s or whatever of f over g's in localizations. And how does it work? Well, you take the localization of z at the set 6 to the I, so you allow 6s as denominators. Okay, and then how can you see that as a regular function? Well, the evaluation around those ideals, right, locally, if you take then the fraction 5 over 6 locally around 0, you should think of it as 5 over 6 in Q. That's how this works. And if you take it locally around a prime, you should think of this as 5 over 6 in Z mod P. For example, it would be 0 if P is 5, right? Because 5 is 0. And if p is 7, then 6 is -1 and 5 is -2, so it should be 2, I guess. Something like that. You get the point. So you interpret the fraction you take, now characteristic free, depending on the ideal you choose in whatever type of field comes up. And you now can do it over all fields at once, which is always usually the whole point of doing scheme theory. You don't have a ground field anymore, you can do it over all fields at once. Yeah, and the brilliance in this construction was to replace a map to the ground field by a collection of fractions in the correct localization. Anyway, I hope you enjoyed this video, and I also hope to see you next time.